In this video, we're going to take a look at several ways to optimize feature selection when doing regression. So we're going to take a look at a couple of these: exhaustive search, forward selection, backwards elimination, and stepwise selection. And there's some utilities that are provided by this book, Data Mining for Business Analytics. I have a notebook with those utilities in it. Because they're part of that book, they're also copywritten by that book author or book publisher. So I'm not going to show the details of those different algorithms, but I am going to show the output and how to use it. So first of all, these models are basically iterating over our features and figuring out which one works best. They're doing it in a similar but slightly different way. So forward selection, we start with 0 predictors or 0 features, and we keep adding features and then evaluating the result. Backwards elimination, on the other hand, starts with all features and eliminates the least useful one at a time. So stepwise is a bit of both. It says, okay, let's do forward selection, and then at each point let's evaluate the predictors that are not useful and eliminate those. And then exhaustive search tries every single combination. But there's a warning with that. The more features you have, the exhaustive search will go exponentially slower. Now, I said it's a factorial algorithm growth rate. I was trying to think what kind of growth rate it actually is. I'm not quite certain it's factorial, but it's definitely one of these here, factorial or exponential or quadratic. Now, why that's important is the input size is the number of features, and the number of computations is the amount of time it takes to compute a result. And so what you see is if you have 1 or 2 features, okay, it can figure it out in a few computations. By the time you get to 10, 20, 40 computations, you're way out here and this line keeps growing. When I was doing a demo with this and I asked people to use exhaustive search, for a lot of people it timed out after numerous hours, and that's just a matter of the number of features you have with an algorithm growth rate that's very steep. It has to try a whole bunch of different combinations before it's finished. So be cautious if you have a lot of features. So some of the utilities provided by our book: AIC score, BIC score, exhaustive search, and then features for each, or functions for each of those optimizing methods I talked about earlier, and then a regression summary to tell you what the results are, and an adjusted R-squared score to tell you what the adjusted R-squared score is. So R-squared is a measure of error from the predictions to the actuals, and the adjusted R-square gives a penalty for the number of features that are used, and that kind of encourages a good balance between getting accurate results and a reasonable number of features, as described here. So let's go. Given the complexity of this one and that I had to pull in a bunch of functions from the book, I'm just going to run it on a subset of Ohio election data. And I have a notebook that's prepared with all of these functions from the book already in it. So first I have the imports that we're going to need. Then, just like our election data before, I'm pulling in election data, but this time I've limited it to only counties in Ohio. Same columns we saw before. I compute the percentage that third-party candidates got in the 2016 presidential election, and this will be linear regression naturally because that is a continuous number, as you see here. The mean in Ohio for third-party candidates was about 4.78%. And now after that, I have all of the utilities from the book in this notebook. And finally, I'll create a smaller data frame with only the features that I know I want to use. In a couple previous videos where I was doing feature selection, there were some I threw out because of cross-correlation or just features that I thought might be a distraction to what we're trying to do. So I've eliminated it down to just a few features: total population, age 29 and under, age 65 and older, median household income, unemployment percent, less than high school percent, less than college percent, and rural percent of the county. Okay, regression summary, and then R-squared score. And finally, this is where we bootstrap everything together. So we have a train model function and then a score model function. And now I'm going to apply the exhaustive search on this one and print out the results. We'll take a moment because it is an exhaustive search. I paused the video. It only took a few seconds to compute that with about 8 features that I've given it. If we doubled that number of features, it would likely take several minutes. If we tripled that number of features, it would likely take several hours. So exhaustive search, great. Just caution if you have a whole lot of features. So what I really like about it, though, is the output that it gives us. We're looking for the highest R-squared scored here. And we typically see it grows and peaks and then falls. So you see the optimal number looks to be right around 5 features, but 4 features, 6 features aren't terribly far off from that, so we can make a judgment call here. As a matter of fact, with 5 features, we see that age 29 and under and age 65 and older are both selected. With 4 features, age 29 and under is selected, age 65 and older is not. I'd be tempted to go with that 4-feature model because there could be some correlation across those 2 columns. If you have a county that's dominated by a college like Athens County, Ohio, that's going to have a higher number of under 25s in it than another rural county. But it's probably also going to have a lower number of over 65s. So I would likely just say, you know what, yeah, I only need one of those columns, so I would go with a 4-feature model. Unemployment percent is not a predictor in those, although it is in a couple other models that we have. Less than college is a predictor, less than high school, median household income. Rural percent is not, and total population is not. So we have a nice table here, and from that we can take a look at the features that we want and make a selection from that, along with using our own judgment. Here I used exhaustive search, but you could certainly plug in forward selection, backwards elimination, or any of the others and get a similar result. So I hope you found this video helpful, and I look forward to reading your comments. Thank you.